over the last sort of 20 years, people have been doing chemical modelings using these force field models. And then only in the last kind of couple of years have we sped up this simulation method. What used to take months amount of time can now be done in just a few hours. So
wow,
humanity as a whole suffers, right? Because that idea is gone into the ether. So the point is, if we pull everything together into a cohesive platform that's super easy to use, if you make anything easier, people will do it more.
Hot new thermodynamic chips could trump classical computers. So apparently there's this new chip to accelerate AI. What are your thoughts? Is this fake news?
We do femtosecond simulations, and a femtosecond is one of the cool facts is a femtosecond to a second is the same timescale as 1 second to 31 million years.
Stop it. Hello and welcome to In the Blink of AI, where I talk to the brightest AI startups and innovators each week. I'm Georgie Healy, and this week I'm speaking to Alain Richardt. He's a New Zealand native and founder of Atomic Tessellator. They're a molecular chemistry and material science platform. Think diffusion models, LLM-assisted research. And for his day job, he's just, casually finding new materials and molecules and helping scientists push the edge of discovery. In one of his many incredible previous roles, he modified NASA's Open Mission Control to drive trading bots instead of the Mars rover. Blue Origin could never. Before we recorded today's episode, Alain said he was happy to simplify what they do at Atomic Tessellator. But when you have someone with the incredible AI and computational chemistry chops he has, you really just don't want to dumb it down. So for the deep tech fans out there, and even the chemistry curious, this show will be a real treat. Now, before we dive in, we do have our live show coming up on the 29th of May. Tickets will be in the description below. I hope to see you there.
You're listening to a Day1.fm show.
Hey Alain, welcome to In the Blink of AI. How are you this morning?
Hello. Thanks for having me. I'm great.
Look, I have so many amazing technical questions because having you on the show, I could not take up the opportunity to pick your brain, especially because we've never had someone with a chemical expertise on the show married with that AI. I am so pumped. I'm going to dive right into it. But before I do, when did your passion for chemistry begin?
I was lucky in that I grew up, I sort of started entering my teenage years at the end of the 90s, and they were still selling chemistry kits that were full of toxic materials and and Bunsen burners and sort of semi-dangerous things. So my earlier memories of early teens and sort of those years were sort of out the back of my house, building experiments, with Bunsen burners and things exploding and things changing color. And
oh, the good old days.
Yeah, the good old days.
Oh my gosh. Do they not use Bunsen burners anymore? Because we had them in my high school. I don't know if they still do.
I think in high school they're still there, but I'm not sure about, the old sort of chemistry kits that children used to buy. And to be honest, I was too young to be burning methylated spirits and, and things like that. But it was all good fun. Yeah.
Can confirm you've got all your limbs still. So clearly you had a natural affinity early on. Look, a nerdy question. What's your favorite element on the periodic table? I have to know.
It's quite a cool question. I probably think molybdenum is because it's not very well known, and it's got some really wild chemistry about it. So,
tell me more. Do you know what number it is, and is it in that weird middle section?
Yes, yeah. Well, some of the cool things about molybdenum is it's a cofactor for nitrogenase. So all of the nitrogen-fixing bacteria that feed all of our plants wouldn't be able to function without it, or nearly as well without it. So it's and the reason I like it is because it's kind of like it's a not very well known silent achiever in the periodic table.
Yes, you're like, I see you. I knew you'd over deliver on that answer. My answer is a little bit more basic, but Mercury has always been my favorite. It's just such a unusual element, right? Just the way it acts and reacts, and also probably because it's so poisonous and deadly. There's some mystique around it. And I know you've got a bit of a story about mercury from back in the day. I think the listeners would love to hear it. Elaine, can you please tell them?
So when I was a teenager, I had a really influential teacher at high school, and Mrs. Jane Clark was her name, and she really accelerated my love for chemistry. And I came one time I came to school with my laptop, and I had a video on it of this pulsating mercury beating heart reaction. And I said I wanted to build this into an electricity generator. So we would set up a standing wave, make all of these things that floated on the surface, and the pulsing mercury beating heart would generate electricity through the mechanical actions of the waves. And
oh my gosh.
It was a crazy idea at the time. Who knows if it's possible? But my teacher really encouraged me, and she gave me keys to the chemistry lab, and I'd be in there every weekend experimenting with mercury, building this apparatus and all of those sorts of things. And like you say, it's kind of wild to think about this because mercury is so toxic. And I didn't really know at the time, but I knew enough to use a fume cupboard, and
thank God.
And I wonder, if that would even happen these days with all of the extra safety regulations and things like that. I feel a little bit sad for the young students of these times. They might miss out on such crazy things happening.
Yeah, there was definitely something exciting about it. Admittedly, this was before my time, and I'm sure I've told you already. We were nerding about chemistry backgrounds. I got a chemical engineering undergrad. But when I worked in a laboratory at a transport and main roads government, it was my first job actually. Yeah, the guys there used to tell me they used mercury thermometers to stir liquid bitumen. And as the bitumen would cool, they'd often crack and the mercury would be everywhere and they'd be scooping it out with their hands and just wild stuff. The good old days. Look, I'm really excited to hear more about what you're working on now. You've clearly always been passionate about chemistry and always been able to take it to the next level. Tell us about Atomic Tessellator and tell us what you're working on.
Yes. So a couple of years ago, I was working at a trading firm, and my boss ended up being a ex-Stanford staff scientist who has a PhD in quantum chemistry, and we became instant best friends. So we were chatting chemistry all the time and swapping research papers and these sorts of things. So I started building Atomic Tessellator off the rekindling of my love for chemistry. It was a side project where I was studying catalysis and mechanical properties of alloys and things like that. So it was weird because I would start work because the trading firm was at 3 in America. I would start at 3 a.m. I would work until 10 a.m. And then I would sleep for an hour, and then I would work all afternoon on Atomic Tessellator.
Oh my gosh.
I did that for a year.
Wow. Some of us watch movies, but yeah, okay, amazing, yes.
Yeah. So yeah, it was cool. It started off, and started studying these chemical systems. I found that all of the tooling to be really, really poor. So I thought, well, we can do better than this kind of as an industry, and I got history as a programmer, so I started making the tooling better and more compatible and easier to use and that sort of thing.
Wow. So it really just started as a passion project and you're like, oh, let me try and fix it kind of thing.
Yes.
When did you kind of start to get a sense for, I would really love to start leaning into this more?
Yeah. So one of the cool things is that over the last sort of 20 years, people have been doing chemical modelings using these force field models. And then only in the last kind of couple of years have we sped up this simulation method. That means that, what used to take months amount of time can now be done in just a few hours. So that kind of speed up really means that we can start to study much more broadly, lots of different systems that are out there, and just experiment with crazy ideas much faster and much more aggressively.
Wow, that's so incredible and so exciting. We may have lost some of the danger and drama from chemistry, but to be able to discover things that much quicker must be exciting. And just for the listener, we're talking force field models. We're already getting really deep on the periodic table. High level, why is this important? What are we doing and why is it important, Elaine?
because this tooling is generally so hard to use, you can imagine there's thousands and thousands of material scientists and chemists that graduate every year. All of these people have great ideas for new experiments and sort of new explorations in their head. But the problem is what actually concrete happens when somebody has a new idea. So if you're a material scientist and you have one of those crazy shower ideas, right? Oh, what happens if we try molybdenum, for example? How do they actually evaluate that? So they get out of the shower, they go to their computer, right, with their crazy new idea. They start trying to use the tools. The tools are very bad. They can't figure it out. They can't get the environment up. They don't know how to describe the system that they're trying to model. And then even if they get that far, they usually give up. And then humanity as a whole suffers, right? Because that idea is gone into the ether. So the point is, if we pull everything together into a cohesive platform that's super easy to use, if you make anything easier, people will do it more. So we want to capture all of those crazy shower ideas and let the scientists experiment better.
Wow, that must feel genuinely really rewarding. There's a lot of rewarding paths, but that's really exciting and really incredible, and probably gives more longevity to those people that pursue that kind of a career. So you've told us about kind of the tooling and how it was quite archaic before. How do you model chemistry with the different methods and trade-offs? I'm sure people would all love to use new tooling, but just kind of map it out in a competitor map a little bit for us, please.
Yeah. So the way that we used to do it for the last sort of 20 or 30 years was called force field modeling, and then what you also have at kind of the other side of that is called DFT. And so these two different models are kind of competing technologies. The force field modeling on the right is where you have a model that's been parameterized by experiments. So people do experiments and they do some simulations and they feed data into it. But the problem is whenever you're fitting a model to a set of experimental data, you have to do an enormous number of experiments for the model to perform well. And then on the left-hand side, you have this DFT, and this thing is based on quantum mechanics itself. So instead of being sort of a model that's learnt from a few different experiments, you have this thing that's based on fundamental scientific laws. And DFT for a very long time has been a very good workhorse of the industry, but you need to have a supercomputer to do it. And breakthroughs just in the last few years have meant you don't have to have a supercomputer to do it. Even a researcher with a small number of GPUs can now outdo what used to take a supercomputer months.
Oh, it's so exciting. And you went there, you started saying quantum. So for the listeners at home, quantum mechanics, people might start thinking of the Hadron Collider, or even not know what quantum versus atomic versus anything else size-wise is. Take us back to high school for a second, Elaine, and tell us what that means.
When we're talking about quantum mechanics, we're talking about actually going from the Schrödinger equation through density functional theory, and then there's a whole bunch of sort of approximations that you can make on top of that. Very broadly speaking, as an overview into the industry, you have the Schrödinger equation, which is a mini body equation for all of the electron activity. The trouble with that is that it's really super hard to compute. And that basically means that it would give you the most accurate answers if you could do it, but there isn't even a supercomputer that humanity has that could do it right now. So we take this next step of doing DFT, which is this kind of intermediate step. It's a more of an approximation, but it allows us to do stuff that's intangible, physical stuff. So there's kind of and then very broadly speaking in the industry, if you've got super accurate over here, and you've got medium term accurate, and you've got low accurate here, it's all for the scientists to choose the kind of trade-offs that they're willing to make. But what we want to do is push away that lower accurate one, because this kind of DFT modeling is becoming more practical for much larger system sizes. So, and because it's based on a fundamental law, you don't have to make so many shortcuts or approximations. So we're sitting in that spot. We're kind of doing scientific computing that's based on physical laws rather than trying to fit some model to abstract data.
There is genuinely a bit of a sweet spot there. That's really exciting. Look, I definitely am thinking in the back of my mind, I really need to invite you to trivia next time because like I feel like you would smash all of the math and science questions. But we're on the In the Blink of AI podcast now, so I'm dying to hear how you incorporate perhaps LLMs into this system. So you've got experience with very large scale systems at Google. Am I correct in saying you're applying some of that experience to how you design Atomic Tessellator's cloud systems? Tell me about that a little bit.
Yeah. And I think one of the really exciting parts about just the last year is that now that we can do these simulations in some cases 100,000 times faster than previous, one of the things that harms material scientists is that they study very simple systems at like 0 degrees Kelvin, perfect crystal systems, and they work in all of these kind of idealized conditions. And reality is not like that. So
I haven't been in 0 degrees Kelvin myself, so
yeah, it makes the math a lot easier, but it's not great for simulations. So what we've done is like now with the rise of cloud computing, Dockerized computing environments, large scale on demand computing, these sorts of things, we can make it so that when you run a simulation on the platform, you don't just describe some single idealized system and run a simulation and get a result. What we do is we inject a certain amount of disorder and we run a large number of simulations in parallel. And what that does is that mimics reality. So if you have a slab of copper or a slab of any alloy material, it's not just a perfect little slab of atoms. There's all this disorder at grain boundaries and certain other macroscopic features. And if you can really easily run simulations, you can inject a huge amount of disorder, run them 100,000 times faster than you previously could, and then get a much more accurate modeling of reality and all of this complexity of reality that you couldn't really do before.
wow. So you're marrying like everything you've learnt technically about cloud computing and being able to run all of those iterations a lot more effectively, right, and accurately.
Yeah, and also the other thing is the material scientists themselves wants to be focused on the material science. You don't want to have to be a distributed cloud engineer as well.
Oh, yeah, such a good point. Such a good point. Actually, few of us do, right? It's a niche interest. So can we get to some juicy stuff? What are some of the most promising applications or materials you might be able to discover? Are you looking for something? Do you have like a white whale of materials that you would love to discover?
Now that we can do these simulations a lot faster and a lot bigger, it means that we can model systems that were traditionally very, very hard to model previously. So some of the really exciting stuff we're working on at the moment is high entropy alloys for the plasma-facing walls of fusion reactors.
Ooh.
So
say that 10 times quickly. Yeah. Okay.
Yeah. Inside a fusion reactor, you've got the metal that is facing like the actual fusion itself. These get bombarded with like neutrons and different high energy atoms, and they have really crazy thermal requirements and just radiation resistance and things like that. And you end up with, and some of these things happen at kind of like tens of nanometers of material, and that way you need to be able to simulate 30,000, 40,000, 100,000 atoms and a neutron bombardment sort of happening all the way through that. And traditionally, an example of this is like in 2001, there was a few really good papers on doing this type of simulation, and it took a whole cohort of global nuclear science engineers to run these types of simulations and get the results. Whereas even now, just a few years later, we can do all of these simulations on a very small cluster here and literally in my house, right? And we can do a whole amount of work that would, in a few hours, that would take globally the scientists to do a year in 2021. So
that is incredible.
Yeah.
Sometimes I hear stories like that and I'm like, I feel really blessed to be working in tech or like in this industry at all, just to hear about these stories. This is just such an exciting time. I do have to ask too, plasma is something that I do find very mysterious and exciting and sexy and cool. Are you interested in plasma in general as well? Or is this something that's not as mysterious and sexy as it was, 15 years ago when I first kind of started learning a little bit about it?
We have to learn enough about it to be able to model the interactions with the matter. Because also the other thing as well is like in fusion research as a whole, it's like the problem used to be with like starting the fusion reaction and maintaining it and these sorts of things, which are still very, very challenging. But actually, I would argue that one of the most difficult parts about fusion now is actually the materials challenge. They actually know how to start the fusion reaction and they know enough about magnetic confinement. But what, like the growing kind of next big problem in fusion is making sure that the actual reactor walls don't disintegrate themselves when the reactor is running.
Wait, why would they do that? Due to the heat and the pressure, or like why would they melt?
Yeah, it's definitely it's just that the plasma is actually giving out so much radiation so what happens is a neutron atom hits the material and it causes what's called these Frenkel pairs, which is like just where a neutron hits an atom, it dislocates it, and then it causes a vacancy in the actual lattice structure, and also and the atom that it's pushed out the way causes another strain inside the crystal structure. So what happens is with these AI models, we can actually predict the amount of strain that this is doing inside the material, and we can actually tell ahead of time whether this is more strain than the material can naturally handle, and therefore it becomes brittle and breaks and all of these sorts of things. So we do all of this actually just only in software, and that saves having to build an entire lab and then do all of these expensive simulations.
Oh my goodness, and wasting the team's time and budget and energy and just breaking it constantly and then being like, oh, damn it.
And the space of possible materials is so huge.
Oh, the space. How much space physically? Like when you say wall, what are we talking here?
Yeah, and we're talking like also the number of things to explore, right? So if you have like you've got the whole periodic table, you might have 20 or 30 elements that have reasonable radiation profiles. You might want to mix between 3 and 6 of them together. Or you might, and then you've got like in what ratios, 20% this, 10% this, these sorts of things. So you can imagine like if you do all of those combinations, suddenly it's just this huge number of things you've got to try. It's not really practical to do it outside of simulation at all. We just need to be able to do huge grid searches on clusters of computers to actually identify candidates.
Oh, I really want to see it in action. Before we move on to the next section, I would love to hear, I'm guessing atomic particles are their own beast, but have you ever run an experiment and gotten, even with the AI simulation, gotten a completely different result, or the AI simulation gave you a completely different result? Like you've got so many years experience. I'm sure your hypotheses are quite on the market, but have they ever been super wrong?
Yeah, it's interesting because there's all sorts of really cool stories in AI about how a model cheats, so you hear about all these funny stories about how the model has learnt some video game exploit, or it's learnt some other way of gaming the system, and we're not immune to that either. So one of the recent examples that we've had is that we have a model that can produce, it can target various types of properties. So what you can do is you can say, I'm really looking for something that has a bulk modulus of 700. Which means that the material is very, very hard, like it's an ultra strong material. If you target, and then we say to the AI, okay, give us some candidate materials for that. And then it tunes away and it spits out like 50, 100 different crystal structures. And then we look at them, and then what we see that it's done is it's just cheated and it's added osmium to all of them, right? So like all of these structures have osmium on them. And that's, although that's a good result in that, yes, the material is super strong, also osmium is currently €3,000 a gram. Right. So
just add gold to the, thanks AI. Yeah, no worries. I'll just do that. Cool. Oh my gosh.
it's going to be one expensive building or something strong, right? Yeah.
Yeah, try get that through the VCs. Like, I just need a
Yes.
couple more mil capital because the AI told me that I needed this. Oh my gosh, that's so funny. We had a previous guest last week who used to be a professional Go player, and he was, like you said about the AI playing games, they'll do a move that no one can understand. Like, that's the most strange / idiotic next step to move. And then you realize, oh, actually they're 100 steps ahead, and then maybe there's like this AGI, ASI next level thing that we just aren't even aware of. So maybe the AI model knows something you don't, Elaine. Like, I don't know.
Exactly. It could be way ahead of us, yeah.
Maybe like through tariffs, it's going to get real cheap or something. I don't know.
Yeah. It could be.
Look, you've been such a good sport, so I'm going to punish you more and make you unpack headlines for us, because most of us see AI headlines around, chemistry or deep tech, and we just kind of take it at face value. So I want to get your amazing analytical brain on some of these headlines and tell us what you think. So the first one, all I'm going to say is, you brought up Schrödinger before. UNSW's Schrödinger's cat. Can you tell the listeners what is going on here? I tried to read it. I didn't really understand what was going on. Please help us unpack this headline.
This kind of backs onto quantum computing as a whole, which is a kind of a really exciting frontier that we need to stay on the edge of. So when I just a few minutes ago, I touched on having like there's Schrödinger's equation, and then there's DFT, and then there's the force field models.
Yes.
One of the and how the Schrödinger equation is very difficult in terms of exponential complexity. We don't have a computer that can do it, these sorts of things. So quantum computing kind of as a whole offers us the promise that maybe we could solve that equation in an acceptable amount of time.
Wow.
What that would mean is that largely all of these sort of shortcuts and all of these models that we're focusing on right now, we could just throw out the window and solve the kind of root physical law itself, which is like super, super exciting. Even when you sort of hear about what are the practical advances of quantum computing as a whole, you always hear breaking cryptography and chemistry. They always say those two examples, and they're absolutely right in both of those. There is going to be a time, hopefully in the next sort of 5 years or less, where quantum computers will be good enough to actually solve the Schrödinger equation, and then all of our tooling will just go out the window because we'll solve the fundamental law ourselves.
Wow. Is this good for you or bad for you? Would this make your day, or be like, oh my gosh, I kind of wanted another decade at playing with the tools?
No, it's a really good thing. We're super on top of it. We've got every couple of weeks, we're kind of running experiments with other quantum computing partners. We've been running systems with quantum variational encoders and helping us solve optimization problems and things like that, because we want to be there to take advantage of it when that click over period happens.
Yeah, you're like, I see it coming and we're ready. That's amazing. Okay, next headline. Hot new thermodynamic chips could trump classical computers. So apparently there's this new chip to accelerate AI. This guy, Guillaume, is building this new chip. What are your thoughts? Is this fake news?
No. These. I think it's super important that we do experiment with these new forms of architectures, and also just anything that can speed up AI in general. So we, just an example of this, we do femtosecond simulations, and a femtosecond is one of the cool facts is a femtosecond to a second is the same timescale as 1 second to 31 million years.
Stop it. That breaks my brain. Femtosecond. Did I say that properly? Femtosecond.
That's 10 to the power of negative 15 seconds.
Oh,
right?
my gosh.
Really enormously short amount of time. And most chemical reactions happen kind of at the upwards. So another example is the proteins in the back of your eyes. They take about 200 femtoseconds to react to light, right? So that's the speed at which this is happening. And we do simulations from femtoseconds all the way up to like hundreds of nanoseconds. So there's quite a large period of time there, but that does actually mean that every day we're doing like 2 million, 5 million inferences through AI, right? So any chip experts that can build a new chip that does AI faster, we're completely on board with, because we're doing millions and millions of these inferences a day through AI, and even a tiny 10% speed up would help us a lot.
Wow. Wow. It's not the same thing, but I briefly talked about you before we started recording about my love of Formula One. And because I watch it at home, I can't really understand, like, they're nanoseconds apart from like the first place to second place, because they're just going at such a fast speed. And I'm trying to imagine it sitting at home, but like they show it on the TV in a way that it looks like they're ages apart, right? But femtosecond, I think that might be above my compute level for my brain.
Not many people even know of that time scale. That's so short, right? We hear of nanosecond, but then down to picosecond.
We worked with nanosecond in engineering. I don't remember femtosecond. That's
pretty crazy,
incredible. There's one more headline: accelerating scientific breakthroughs with an AI co-scientist. Please tell me a little bit about this one, Alain.
Yeah, I feel like this is the biggest, sort of most exciting one in general. And it's also an area that we're focusing on a lot. So one of the, AI fundamentally is like the mechanization of thought, right? So if you can have like an AI co-scientist that can help you review a paper, form an alternative hypothesis, and even run some of the experiments, that really takes us back to that earlier ethos of what we wanted to do for a materials scientist. So if a materials scientist can walk up to their computer and say, hey, I just read this paper, can you reproduce the work in it? Then the AI co-scientist will actually run the simulations, will reproduce the work, will interpret the results, and then come back to you saying, I was able to rerun these simulations to create what was in this paper. And then the scientist can say, okay, rerun the whole thing again, but this time swap out all copper for aluminium, go. Right? That's what we want to get to, right? We want to get to the point where we can just say to the machine, go and try this experiment, and it will go. So AI scientists, a couple of months ago, I gave a talk in Riyadh at the Global AI Conference in Saudi Arabia, and I had our first version of this running. So we have Atomic running internally, which is able to review a paper and then set up and run simulations. And while I gave the talk, I set it on the great big projector behind us, and the crowd was able to watch the AI agent actually build and run build a set of hypotheses, import the data structures, run all of the simulations, and then come to the result while I was telling about, the future of AI and materials science.
And so much of this, I'm sure, is hard to imagine without seeing it, right? So being able to actually see the model, explain what it's doing and go ahead and do it, that's incredible. So exciting.
Yeah, it's very visual. It's nice to be able to summarize into the points of the AI, and then that we have a system in the platform as well where the AI can write notes, right? So the AI writes a couple of little notes about what it's thinking, and then it runs the experiment, and then the results come out. So it's all live on the workbench.
Alain, can you make an LLM that creates like lab-grown, precious jewels and things? I know we can already make lab-grown diamonds and certain things, but there's certain inclusions that are in, say, an emerald, right? And if you do a lab-grown emerald, it just doesn't look the same as a real one. Not that I have real ones lying around in my house, but like these are the things I want to simulate. Like, how can you make it really look like heritage, Sri Lankan sapphire or something like that? That's what I would be doing the models on.
Yeah, definitely. Yeah, and those kind of so often reality in terms of like all of these like gems and how alloys perform and things like that. They are it goes back to like just imperfections. So instead of being able to model very simple systems like a pure slab of copper and things like that, you need to be able to model all of the different types of defects and dislocations and impurities and all of these sorts of things. So in a materials science platform as a whole, you need to be able to sort of say, these are the parameters that you want to operate within. and then the system will generate lots and lots of different imperfections and then average the results towards the end. And that's how you go from like something that's just too much theory in terms of like a pure system that's really basic to something that really reflects reality.
Yes. Look, we've talked about your background as as a very deep domain expert in the chemistry field. We've also talked about your technical background and working at Google. But as a founder as well, I'm curious to ask you a couple of questions. Like, you're breaking ground here with Atomic Tessellator. So how do you measure success? What are you looking for? Is it the number of new materials you discover, or are there other metrics that you're really focused on at this stage?
Yeah, so for the last, I would say 4 or 5 months, we've been working on what we call experimental parity. So what we do is we take a bunch of very high quality lab data that says that these particular materials with these particular ratios have these mechanical properties, have these electrical properties, have these thermal properties, these sorts of things. And we've been making sure that our simulations match reality.
Wow.
So there's always this trade-off between like accuracy and computing speed. There's two levers that you're pulling all the time. And what matters is that you can do stuff fast enough so that you're not costing a lot in terms of computing power and bills, but also accurately enough to reflect reality. So when we started, we were doing things. We have these parity graphs that show like reality versus predicted, and when we started, we were all over the place.
Scatter plot. Okay. Yes.
And then we've been refining, and now we're well past the point where we can be confident in our own predictions, and for not just simple systems, but complex systems. Yeah.
So you've got to have a new goal now. You've nailed that one. Well done.
So now that we're confident in our predictions, we actually have a bunch of new ultra strong materials. We have some radiation resistant materials. We have a bunch of materials that we've actually predicted, and we're working with the labs now who are synthesizing them and like proving that they'll work in reality. But I'm not actually at all worried about that, because our like previous predictions are so accurate compared to all of the other lab results that I know it's going to be close enough. So
I'm asking really trivial questions here, but do you get to name any of the new materials you come up with?
Yes,
you do?
Yep.
Oh my gosh. Okay, you've got my email. I want to know all the cool new names. I can drop them in sentences. I'll be like, I met the guy who invented or created, or I don't know what it is, whatever you call it. That must be fun.
Yes.
My grandfather was a town planner in Brisbane back when there were like hardly any houses in certain areas. He had so much fun naming stuff after like family members and stuff like that. I bet you have a ball.
Yeah. We have like all of our systems, all of our internal things are all named after various video games and actually Atomic Tessellator itself is named after an object in a video game, right? So
oh my goodness. I love this thing. You deserve it. You should call it whatever you want. That's very well earned.
It's cool because like we were also inspired by, there are other companies that have done this, like US Robotics is named after the Isaac Asimov novels. Oracle was a sci-fi name. Like there's a lot of history of great companies being inspired by sci-fi, and that's what we want to try and do as well.
Just anyone that says there isn't a lot of emotion and heart behind it is wrong. Look, I would love to hear how you hire, Alain, because, the deep knowledge and understanding of AI is one thing, and then there's the material science aspect. How do you find people in the space?
Yeah, it is super difficult. So we're a New Zealand startup in the sense that the company is here, but I'm actually the only employee in New Zealand.
Good for time zones, I'm sure.
but it's cool being a remote company because we get to choose the best from everywhere, kind of around the world. What we have found is that it's certainly easier to teach a programmer physics than teach a physicist programming. So we tend to go heavier on the programmer side first, and the science can be picked up. But also one of the other things that we really, really value internally is like a growth mindset. So anybody in the company can challenge any idea. I expect a certain number of experiments to fail within all of our staff, right? So if somebody is if somebody is working here at Atomic Tessellator and everything they do is successful, we encourage them to be more ambitious, because that means that there's even greater greatness in them. So we try and bring that out. And I remember sort of from my careers, being at large organizations like Google, where I managed, 20 people, 30 developers, that kind of thing in my history. I kind of lost a little bit of that throughout my career as a senior programmer as well. And now I'm rediscovering the joy of managing incredible people. Like, it's just so amazing to see all of the staff members come back to me and be so excited at the things they're discovering and the new sort of frontiers they're pushing. And
it does sound rewarding. It really does.
And also with everybody in the company, everybody has their own internal stretch goals, right? So you have the amount of work that we have to do, and then you have some crazy ambitious plan that's aligned with the person's career, right? But also is like a crazy stretch goal. And when the staff, like, the staff can see that the manager is interested in the person and growing them as well, they kind of get excited about what crazy thing can I invent or come up with. So
I have a sense that the environment's fantastic also, Elaine, because you're clearly so on the tools yourself. You're not kind of standing back and just like, tell me what you guys come up with. Like, it's so clear that, like, before we even started recording, I was like, oh, there's a bit of background noise, and you had all these servers running. Like, clearly you're like in it, you're doing it yourself, and you're just as passionate and excited to discover and create yourself. I really get that sense.
Yeah, I've got a server rack here in my house. There's a big sort of full rack unit right beside us. And yeah, I mean, my electricity bill, I think, is about 6%, the national average. Yeah.
Look, there's a laptop behind you. You're on a computer speaking to me. I can only imagine what would happen if I zoomed out. It would be a war room in there, I bet. Yeah. Look, this is my favorite part of the interview. This is where we go into hot takes, spicy questions. Are you ready for the last part of the show?
Yep, sure. Yeah.
Periodic table mugs. Those mugs with the periodic table printed on them. Are these cute or lame?
Cute.
Thank you for saying, because I actually had one for, I think, a decade there for a while. So you nearly made me cry. Do you have one right now or no?
No, not a periodic table mug, but we've got periodic table everything, a towel, like different stuff that and we've actually open source modeled a whole bunch of materials for our open periodic table as well. So
hot tip.
When we interview scientists, they actually comment that they keep going back to our periodic table and using it because it's like has 3D models of each of the elements, crystals spinning and cool stuff like that. So
can the listeners see this if we put a link in the show notes?
Yep, sure.
That would be amazing. Would love. Okay, guys, we're going to have that in the show notes. If you were to make an Atomic Tessellator cocktail, what would go into it?
Yeah, that's quite an interesting question. I think probably something like gin, because it's kind of sort of sharp and a very distinct taste. And then also, just for the chemistry, maybe some lemon for acidity.
Lemon and gin. It sounds fresh. It sounds unapologetic. It sounds honest. It's an honest cocktail. You know what you're getting. No hidden, agenda in there. I love it. I feel like this is something that everyone could get on board with. Very on brand. I have a feeling you would be snapped up, Elaine, if I'm honest, by any of the tech companies. They would be desperate to have you in one of their executive roles. You could do that. So why go this hard path of being a founder?
It's a really nice question because it kind of touches at what you are as a person. So I was always, ever since I was young, I was a bit rebellious and a wee bit sort of against the grain. And working at these large corporations taught me a lot about people management and skills and large scale engineering. But really, I like having the freedom to do our own thing and push at the boundaries a wee bit more. So having your own startup is like definitely on hard mode, taking the hard route. But it's just so rewarding seeing the staff grow, seeing the company grow, making new discoveries at the rate we are as well. So every week we're finding some new angle or partnering with somebody new, and they have a set of challenges that are just really wild. If I may, just one very cool example was just 2 weeks ago, I was at the NVIDIA conference over in San Jose, and I just serendipitously met a professor from Stanford who told me about this very special structure inside the shell of mollusks called mother of pearl, and it's this very special material, right? But what it does is it's actually built in such a way that stops crack propagation. So you have these little wee microscopic discs that are really strong in one direction. They get cracked or hit from a strong impact and they break. But because due to the way that they're set in this matrix of material, that crack doesn't actually propagate like when a crack is in glass, it propagates. When a crack is in metal, it propagates. But this kind of nature's kind of figured out a way of preventing crack propagation. And these kind of things that you have as a founder, just going to all of these new meetings and saying, what are you doing? And these amazing, sort of ideas that come together. We immediately went home, jumped onto Atomic Tessellator, started running all of these simulations, found even better ways that we can improve it. And we think that there's this sort of bio-inspired anti-crack propagation material that we can even start experimenting with. So
that is so fascinating. And you do hear about this happening, right? Like people studying like even airplane flight by being inspired by birds and things like that, and shapes and taking things from nature.
Yeah, nature's had so long to figure out these kind of problems. It's amazing how we can get inspired by them.
And mother of pearl's really pretty too, so
yes,
might make everything look really nice and shiny.
Yeah, that's true. Yeah, that same color, that iridescent rainbow color that's produced is actually an artifact of this really crazy structure that's also super hard and stops crack propagation. So, yeah, it's really cool. Yeah.
Thank you for sharing that. I'll never look at it the same way again. That's incredible. So what do people get wrong about you? You're from New Zealand, you've got this startup in chemistry. What don't they get right about you, Alain, do you think?
I think because we're kind of not in Silicon Valley, we kind of tend to get dismissed a bit more. But that's okay though, because also it does mean that it motivates us a lot more. So I definitely think we're kind of the ragtag team of we're kind of weird outsiders.
Yeah, there's power in that, right? There's a lot of power in that. I love it.
Yeah, and also the other thing is we don't really worry about doing large amounts of marketing and things like that because we let our results speak for themselves. So yeah, we're just kind of like the misfits on the outside of material science.
I love the honesty of your answer. It's also kind of like it doesn't really matter if they don't get it, you know what I mean? Because the proof will prove itself.
Yeah, and one of the things that I found really kind of inspiring was I heard the story about Larry Page and Sergey Brin when they started Google. What they would do is they would go to an investor, they would explain Google to them, and if they didn't get it, they would just move on. And they would say, if the investor doesn't get it, 10 more minutes of me explaining it isn't going to make you get it, right? So
words to live by.
You'll find you naturally attract people in investors and in staff and in things like that you vibe with. So it's about not forcing the universe and just letting it go where it will.
We have a lot of founders that listen to the show. I think that's brilliant advice. Thank you for sharing it. We've got one last question. What's one headline that we might see in 2025?
One of the cool things that's coming up is declarative materials. So basically, one of the holy grails that material science and maybe us is coming to soon is being able to say, instead of being able to say, here's a bunch of materials with all these different properties that we want to simulate, we actually flip it completely over and do it what's called inverse materials design, where we say we need a material that has this radiation resistance profile, this conductivity, this thermal stuff, and then the AI will just produce it. So we declare what we want, and then the AI fills that declaration of properties. So that's something that I think is coming within the next 2 years, certainly.
Declarative materials. You declare what you want, the AI will just generate that. That's incredible. Heard it here first. What a way to end the show. Alain, you've been such an amazing guest. Seriously, I genuinely feel privileged to have been able to speak to you. Thank you so much for coming on the show. Before I let you go, is there anything you can shout out to the listeners? Anything they need to know? How can we follow you? How can we see what's coming next for Atomic Tessellator?
Yep, sure. Thank you. So at the moment, we're approaching general availability for the platform. So that means that if you're a researcher or if you're a university student or you're even just an enthusiast looking into material science, then please reach out. We'll bring you part of our beta user program. We'll give you some credits. We'll give you platform access. We'll give you sort of primary support and help so that we can grow it. And then also on the investor side, so we are raising a seed round at the moment, and we're looking for investors who are deep tech and also an interest in material science, because this sort of field is growing a lot this year. So we're super excited to hear from anybody in any of those areas.
Amazing. I think there will be a lot coming up. So definitely we will all be following you on LinkedIn and can't wait to see what's next for the company. Thanks so much for being on the show.
Thank you as well. Thank you for having me.
Thank you for listening to In the Blink of AI. You can check out the show notes for anything discussed in this week's episode, and we will be back next week. This podcast was produced by Day One, with music by Dan Hansen and visual artwork by Sophie Tyrell. If you loved the episode, please tell your mates. And I love AI news. Please share your thoughts and suggestions to georginarosehealy@gmail.com.